Hi, pre-calculus students. Welcome to my kitchen. I do have some food cooking. You might hear some beeps. Super hungry, but I really wanted to do this video for you. This is Guided Notes 2.6. I did put notes in your hand, and I did also put them on Schoology in case you need to print them or look at them electronically. So we're going to do these together today with my writing tablet. I'm going to do my very best. I may have mentioned to you my writing with the tablet looks a little bit like a kindergartner, but we'll do the very best we can. Also, I have my calculator with me, and I believe you should have your calculator with you too, or your phone, so that when we are graphing the notes here, that you're graphing them pretty accurately. Of course, when I do it with my writing tablet, it may or may not be as accurate as it could be. So, to really get a good picture of the graph also, besides my drawing, have your graphing calculator too. So I'm going to go ahead and share my screen here. And let's see, there we go. And just going to pull myself over to the side here. And so pre-calculus guided notes 2.6. So you noticed in calculus, pre-calculus, we don't do many guided notes, but this chapter is perfect for it. So what happens is in Algebra 2, in Chapter 8, the dreaded Chapter 8, you did rational functions and you looked at horizontal and vertical asymptotes using the graphing calculator, okay? Now we're in pre-calc, we are going to find horizontal and vertical asymptotes on our own without a graphing calculator by looking carefully at the rational expressions given to us. We are also going to find slant asymptotes, which I think is not in Algebra 2. And then we're going to be graphing our own rational functions without a calculator. So again, I'll do my very best to do that with my writing tablet. So let's take a look here. So number one, a rational function is a fraction with polynomials in the numerator and denominator. When you look on 2a, 2b, and 2c, you can see that that's true. We call the function generally f of x, and the numerator, the polynomial n of x for numerator, and the denominator d of x for denominator, so that we don't have to keep writing out the words numerator and denominator. So we study rational functions because they make up many important formulas, and they also occur when variables are related inversely, when one variable goes up and the other goes down. So as you can imagine, this happens a lot. So the question is, we're going to take you from Algebra 2 to pre-calculus. So 2, how do you locate vertical asymptotes? We call those VAs, vertical lines a graph curves toward but does not touch, in the form x equals c. So when you provide a vertical asymptote, you just don't put the x where it's located at, like 2, you put x equals 2, because the vertical asymptote is a line. So we write the equation of a line. So how do we do that on our graphing calculator? Well, this is what we did in Algebra 2, right? So let's take a look here. See, so on A, I'm just going to give a quick sketch. There's my microwave. Of 2 over x minus 3. Hopefully you put that in your calculator, and so that you can also sketch it. Wow, am I bad at that? There we go. And then that is coming through, doing my best here. Okay, I've done better, but hey, that was my first one, right? Now, it turns out then that the vertical asymptote, where the graph seems to be going vertically, would it be at this dashed line right here, which is x equals 3. B, find the vertical asymptote of x minus 2 over x plus 6. So what you see here is that when you do the graph on the calculator, it looks something like this. That was supposed to be a smooth curve. I can do better. That's okay. Right, you have your calculator with you, and there's another branch up here. Okay, like that. Sorry, that was so bad. So you know what? Let me try erasing. Can I erase? Let's erase. Oh, that's nice. There we go. Taking time to erase. There we go. And let's try this again. So it seems to go Oh gosh, that's so much better. Whoops, and now it put something different there. Oh well. Okay, so, and if you look, the graph seems to be going vertical. The graph seems to be going vertical at x equals -6. There we go. Sorry, my writing tablet does a couple little things that I'm not always used to. Now, C, find the vertical asymptotes of -1 over x squared minus 3x minus 4. Not that you need to do this, but I just want to point out, and if you would write this also, that if you factor the denominator, again, not necessary to graph, right? But it would factor to x minus 4 and x plus 1, right? We're used to factoring quadratics. Now, this graph has two vertical asymptotes. I'm going to do my very best to graph it here. So let's see. There is a middle part that kind of goes like this, right? You're putting it on your graphing calculator too. There's another one here. So it actually has 3 branches and then one here. There we go. Wow, I actually did that better. And we would find that the vertical asymptotes at these dashed lines here seem to occur at x equals 4 and x equals -1. Okay, so the big question is that's your algebra 2 part. The big question is conclusion. How do you find the vertical asymptotes without the aid of a graphing calculator, just by examining the rational function, meaning looking at your rational functions here, right? And deciding where the vertical asymptotes are. Well, take a look here where the vertical asymptote is x equals 3. Take a look at the denominator. It has an x minus 3. On B, the vertical asymptote is -6. Take a look at the denominator, x plus 6. On C, the vertical asymptotes are located at x equals 4 and x equals -1. And look at the factored form here. So when you take a look then, it would appear that vertical asymptotes occur at the x's that make a denominator 0. And that's what we're going to write on the conclusion. They occur at the x that makes the denominator 0. D of x equals 0. Right, so now if I gave you rational expressions, asked you where the VAs are, you could just look in the denominator, find the x's that would make the denominator 0 and go, oh, there's VAs there. Okay, there's a little bit more to it, but that gets us started. Number 3, how do you find x values of a rational function where holes are located instead of vertical asymptotes? First, using a graphing calculator. So it turns out that there can be holes in a graph where at one x, there's not a y, there's a hole instead of a vertical asymptote. And what does that look like? So what you do is you actually, the best way to find a hole on a graph is to graph it on your calculator and then look at the table. That's the best way to use it using a graphing calculator. So I'm going to write that right here. That would be, again, how do you find x values of a rational function where holes are located instead of vertical asymptotes? First, using a graphing calculator, of course, then we're going to transition to none. And go to table, where you see x's, where for y it says an error. But there's no VA there. So if you go to a table and you look at the x's where the VAs are, of course it will say an error because the graph is approaching that x value, but is never hitting it. So holes, the same thing happens. You go to the table and you look for the x where the y has an error, but then you say, okay, but is there a VA there? or is that a whole? And so that's what we're talking about here. Now, 3a says find the wholes of this expression. So what we're going to do is factor it, and that's going to help us. So the expression factors the numerator to x plus 3 and x plus 1. And the denominator, that's my food, factors to x plus 1. Oh, it doesn't factor, it already is, isn't it? Okay. Now, when you graph the original rational expression or the factored on your graphing calculator, it looks something like this. That was supposed to be an open circle there. I did my best. Sorry for the pause. There's a hole where x equals -1, okay? And again, a great way to go is to go to your table. Now, when you graph this graph, notice that there's no VA. Nowhere does this graph go vertically. So where this x is, when you go to your table, when you go to where x equals -1, and you look at the table, it shows that the y has an error. And the graph on your calculator doesn't do a good job of showing this hole, but certainly there is one there, and so we draw it there. Okay, let's go to B. Let's practice again. Let's find the holes of this rational expression. Notice, by the way, on A, that I'm not going to scribble them out, but notice that the x plus 1 in the numerator and denominator does cancel. Now let's go to B. Let's take a look. The numerator factors to x plus 5 and times x minus 2. And my denominator factors to x plus 5 times x minus 1. Notice that the x plus 5s do cancel. That may be important to us later. Okay, let's go ahead and graph. And what ends up happening is there actually is a VA. When you graph this expression, it does have the 2 branches, and it looks something like this. Here we go. I could have done better. It actually goes through the 2, right? And it looks something like this. Okay, but when you go to your table, you do see that where x is a 1, that there is an error for the y. And when you go to where there's another error at x equals -5, there's an error for the y. But we can see that there's a vertical asymptote at x equals 1, but there's not one at x equals -5. That, in fact, is a hole, right? So our hole is located, we're only going to put -5 because the VA is at where x equals 1. So again, look at your -1 where the hole occurs for x, and look at your denominator, x plus 1. On B, look at where the hole occurs at x equals -5, and look at your denominator, right, in your expression where the x plus 5 was crossed out. So it turns out, in conclusion, that holes, in bold here, rather than vertical asymptotes, can be found with the aid of a graphing calculator, well, without, that's supposed to say, without the aid of a graphing calculator by locating x values in a rational function where the x makes the denominator 0, but it cancels. But the factor cancels. Okay, so this means, in conclusion, a vertical asymptote occurs at an x that makes the denominator 0 and does not cancel. A hole occurs at an x that makes the denominator 0, but the factor cancels. This means we have to go back up to vertical asymptotes and add to it. Here we go. Vertical asymptote, x makes the denominator equal to 0 and does not cancel. There we go. So again, now we can look at rational expressions and find vertical asymptotes and holes, right? Without graphing or without using a graphing calculator. Number 4, how do you locate horizontal asymptotes? Those are horizontal lines the graph curves towards but does not touch. Those are in the form of y equals c on a graphing calculator. So again, A, B, and C, this is the algebra 2 part, right? You used to find horizontal asymptotes using your graphing calculator. So again, take a look. We've already graphed 2 over x minus 3, right? And that was, let's see if I can do a good job with that again. Here we go. There we go. And oh, I'm getting a little better at it. Now, it would appear that a horizontal asymptote, where the graph goes horizontal, appears to happen right on the x-axis. That's where y equals 0. Let's see if we can find an HA, the horizontal asymptote of 3x minus 2 over x plus 6. So when you graph that in your graphing calculator, it has a little branch up in the corner and it goes through, let's see if I can do this pretty well. Oh, sorry, touched something I wasn't supposed to. There we go, and goes through here. Okay, so it would appear, and it's kind of hard to tell in this case because of my drawing, but it would appear that the graph does seem to be going horizontally. You know what, actually I can do a better job here. Let's erase a little. Thank you for hanging out with me and bearing with me on this. Here we go. That the horizontal asymptote seems to occur, seems to flatten out about right there. Let's try that again. There we go. And that would be, if you looked on your graphing calculator, about where y equals 3. Okay. Last, let's find the horizontal asymptote where the graph seems to be flattening out on the ends for the graph of x squared over x minus 1. Now this graph has a kind of unique look to it where it goes like this. So it turns out nowhere for this graph does it seem to flatten out horizontally. And so there's not always a horizontal asymptote, just like there's not always a vertical asymptote or there's not always a hole. So what can we do here instead of using our graphing calculator to identify horizontal asymptotes? This is a little harder, but it kind of makes sense. Okay, let's go a little further. How could I use algebra instead of a graphing calculator to locate these horizontal asymptotes? And actually, the answer to that is right below. So, horizontal asymptotes can be located without the aid of a graphing calculator by either using substitution of a large value of x in the function or by these logical rules. So, you can substitute a large x, right, into the function, right? Or we can use our rules of logic. So the answer to the question, if you just draw arrows, is above, okay? And here's what I want you to see, okay? Let's go back up and then we'll fill in our 3 rules for horizontal asymptotes. Take a look at A. The degree of the numerator of A is 0. And the degree of the numerator of the denominator, so let me say that again. The degree of the numerator is 0. The degree of the denominator is 1. And we found that the horizontal asymptote was at y equals 0. Okay, so let's go on down. Here we go. I feel like I'm getting worse at this. So here's what I want you to know. If the degree of the numerator is less than the degree of the denominator, just like you saw on A, then the horizontal asymptote is y equals 0, is the x-axis. Let's just take a quick look why. Take a look at this fraction here. Now, when you're talking about horizontal asymptotes, that's graphs that flatten out on the left end or the right end, right? That's where the x's are getting very small or very large. If you put a very large x into this denominator here, and I mean like 1,000, 2 divided by 2,000 minus 3, 1,000 or 2,000, this fraction is going to be really close to 0. If you made the x even bigger, like 100,000, 2 divided by 100,000 minus 3 is going to be that fraction even closer to 0. So, and that function is the fraction, right? That's a y. So as x gets very big, this y value of the function approaches 0 because the denominator keeps getting bigger and bigger while the numerator is not. Okay, let's look at b. Notice that the degree of the numerator and denominator are both 1. Okay, let's fill in this rule and then we'll go back. So here's b. If the degree of the numerator is equal to the degree of the denominator, the HA is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, here's what I mean. Let's go back up. So the degrees of the numerator and denominator are equal. And so we are going to divide the leading coefficients. 3 divided by 1, notice that's where we found the horizontal asymptote. Why is that true? Because as a function flattens out on the ends, as x gets very, very large or very, very small, they tend to cancel each other out because they're the same power, and it just leaves the ratio of the leading coefficients. Let's take a look at C. Notice we didn't find a horizontal asymptote. Notice that the degree of the numerator was higher than the degree of the denominator. In other words, as x's get very large, the numerator keeps getting bigger faster than the denominator, and this whole fraction just keeps getting bigger. It doesn't head towards a y value, it just keeps getting bigger. And that's our third rule. If the degree of the numerator is greater than the degree of the denominator, then there is no HA. Okay, now this brings us to then the slant asymptote. If you look here on this graph, it actually on the ends up slanted. So that's what we're going to do next. But let's just recap horizontal asymptotes. So now with our rules below A, B, and C, we can just look at the rational expressions and find the horizontal asymptote by looking at the degrees of the numerator and denominator and the leading coefficients without using our calculator. Welcome to pre-calculus. Next, number 5, how do you know if a rational function has a slant asymptote? We call that SA. It is a line of the form y equals mx plus b that a graph curves towards but does not touch. So let's go ahead and graph again, right? We just graphed on we just graphed that for horizontal asymptotes when we were looking for one and didn't find it. And it went like this. There we go. Let me try that again. That's not what I meant. Let's see. Well, looks like it's just going to want to stay there. And let's go to the vertical asymptote. Let's see if it'll let me erase that. I'm not sure how to, I feel I should know how to get rid of that. Oh, well, we'll just leave it there. Sorry about that. I don't want to mess it up. At least we can see it. And like this. Okay. Now, let's see if I can go ahead and get rid of that. There, I can do this again. I think I've got it now. took me a little bit. You can always fast forward when I'm struggling. So does a slant asymptote of this graph occur? We're going to say yes, it does, because it seems to be slanted on the ends. When you graph for B, does a slant asymptote of 2x cubed minus 1 over x squared plus 4 occur? And when you graph that one, you find it has this really kind of cool, it goes like this. In other words, it really does slant on the ends also. And so we're going to say yes. So conclusion, how do you know when you'll have a slant asymptote? So that will occur when, take a look at the numerator on A. The degree is 2. Take a look at the denominator on A. The degree is 1. Let's go to B. Degree of the numerator is 3. The degree of the denominator is 2. So a slant asymptote will occur when the degree of the numerator is exactly 1 higher, not more, exactly 1 more than the denominator. Okay, now we know how to find horizontal and vertical asymptotes, right? So how do we find the slant asymptote in y equals mx plus b? Well, guess what? Here's what you do. It is division. I'm afraid so. I mean, when you look at these rational expressions up here, this is actually a division problem. X squared divided by x minus 1, 2x cubed minus 1 divided by x squared minus 4. These are actually division problems. But because we just need the slant asymptote of y equals mx plus b, we just need 2 divisions. We do not need a remainder. So here's what I mean. Let's actually go ahead and do the division. Okay? And our quotient will be the y equals mx plus b we're looking for. What would I multiply x by here to get x squared? That would be an x. That would be x squared minus x. Here we go. I'll subtract. And I'm left with a plus x. What would I multiply x by here to get an x? That would be plus 1. And we have the slant asymptote right there. If you graphed x plus 1 on this graph right here, it would, in fact, you would see the graph go right towards it. Now, to do the division for b, 2x cubed minus 1 divided by x squared minus 4, I need a little bit more room. Let's see if I can go to the edge. Let's try it. Let's see if I can do that here. Kind of small. X squared, that's a 2. Minus 4. And our division is 2x cubed minus 1. Okay, that's a little too small. I'm going to go below. Here we go. I think I had some room down here. I sure do. Let's do that right here. So that was x squared plus 4. And 2x cubed minus 1. And again, our slant asymptote will be the quotient. What would I multiply x squared by to get 2x cubed? That would be a 2x. And then I'll fully multiply 2x cubed plus 8x. Then I'll subtract. There we go. And I have negative 8x minus 1 left. Now notice that this is a remainder here because it's less than, the degree is less than the divisor. So I have y equals 2x. What's my b? Plus 0. Right? So we don't use the remainder, but because I need 2 parts for y equals mx plus b, I have a 0. You would find if you graph y equals 2x plus 0, on the above graph be that the graph curves on the ends right towards that line. And let's go ahead and write our y equals x plus 1 right here, fill everything in. So I'm sorry this has been such a long video. I'm sure that you may want to divide it into a couple pieces, and we do have one piece left and then we're done. Number 6, how do I graph a rational function then without the aid of the calculator? So the first thing you do is factor the numerator and denominator, right? That way we can see better where vertical asymptotes and holes are, right? So we'll find the vertical asymptotes at the x's that make the denominator 0, and we will graph that. We'll put dashed lines to remind us that it's there. Write down the graph. Okay. Then we'll find the HA or the SA. Notice that it's one or the other. Either the ends end up slanted or they end up horizontal, right? And we graph that on the ends with the dashed line. We don't make it go all the way through the graph because the graph can cross a horizontal asymptote, just not a vertical. So just on the ends. Then we'll find x-intercepts, right? X and y to help ourselves, right? We know how to do that. And then find more solution points where we're like, I'm not exactly sure what's going on, just to get a smooth curve. Okay, so let's take a look. For example, so let's do our steps here, okay? We are going to graph 4x minus 1 divided by x minus 3 on our own. Here we go. First of all, we're going to factor, but notice the numerator and denominator are already factored, right? So I don't have to worry about that. I checked it off. The VA, right, would occur at x equals 3, right? Because that is the x that makes the denominator 0 but does not cancel all the way across the graph. The graph, in fact, cannot cross that vertical asymptote because it's a domain issue. C, let's find the horizontal asymptote or the SA. Let's compare those degrees. The degree of the numerator is 1 and the denominator is 1. So the HA must be the fraction or the ratio of the leading coefficients, 4/1 or 4. Okay, so that means on the ends of the graph only, I'm going to put a dashed line at y equals 4 and show how the graph is supposed to end up. Let's find x-intercepts, right? So x and y-intercepts. So the y-intercept, of course, where x is 0, right? We've done that. When you put a 0 into the function, let's see, you get a 1/3 out. Okay, so let's graph that y-intercept, 1/3. Oh, it doesn't like me to do that. I'll just put a dot there. The x-intercept is where the function equals 0. Okay, don't let that mess with you. I'm going to come on up over here and do that, right? So where does this function equal 0? Notice we've already done that. A fraction is 0 when its numerator is 0. So I just need 4x minus 1 to equal 0. So I'm going to add a 1, divide by 4, and that x-intercept is at 1/4. Here we go. That's very small, isn't it? Okay, and then find more solution points. Okay, let's see what I have so far though. So at the bottom here, notice that on the left, my graph has to end up coming up towards this horizontal asymptote. And I know that because it has to go through these 2 points, these two x and y intercepts, and it has to come down towards the vertical asymptote. So I know all what's going on here at the bottom of the graph because it has to go through these points, those intercepts, and because they're lower than y equals 4, it has to go up towards those and continue down towards the VA. Now up here, right, we know the branches are like opposite each other. I'm not sure what's going on, right? Is the curve down here, right between the VA and the HA? Is it up here between the curve, you know, the VA and the HA? This is where I need a solution point or more. So let's pick X to be 6, right? Here's where X equals 6. And let's put it into the equation and let's find out what Y value we have. So that would be 4 times 6 minus 1 over 6 minus 3. So let's see, that would be 24 minus 1 is 23. 23 divided by 3. So we're going to have to estimate a little bit, right? No problem. This is just sketching. 23 divided by 3. Well, let's see, that would be about 7 2/3. Yeah, so the point I'm going to graph is 6 and 7 2/3. Here we go, 6 and 7 2/3. Oh, I see. Okay, so the graph then, the other branch is above here, and it goes through this point, it goes up towards the VA and down towards the HA. And there we go. If you put this function on the graphing calculator, you'll see that you actually did a really good job. So thanks so much. I know that took a lot. Probably had to take breaks in between. Now, please understand when I see your 2.6 homework, if I just see sketches where I obviously don't see any VAs or HAs or points like you just copied from somewhere, I can't accept that. I have to make sure I can see enough information to know that you really were doing this. So thank you so much. And I'm going to stop the share and have a great day.